Now, this problem essentially looking at a graph, and it tries to attach some meaning to the edges and to the vertices that are in the graph. And we say that we are going to model dependency or precedence relationship. So what it means is that we are going to use directed graphs where there are directed edges, and the direction includes indicates the direction of dependency. Now, what is an example of something like that? For example, courses in the university, right? So we have prerequisites. So you must take A before you take B, for example. In that case, then you will draw an H from A to B, indicating that B follows after A. Or it could be task scheduling. So it could be that you're a project manager, it could be construction, it could be IT projects, where you need to do different tasks, but there are dependencies between the tasks. So you can't do all of them at once. You need to do A first before you can do B, so that you can do further tasks. It could also be causal or temporal relationships. It means if something happens at a later time versus something that happens earlier, there may be some dependency between them. Now, the one thing that we want to avoid is a cycle. So in this case, A leads to B, B leads to C, C leads to A. Now, when you have a cycle, you have a deadlock, right? So imagine that you have a project, and then you ask A, have you done the stuff? Well, I cannot do my stuff because I'm waiting for C. Then you go and ask C, or C says, I haven't done it because I'm waiting for B. B says B is waiting for A. So nobody is doing anything because everybody is waiting for someone else, right? So there is a deadlock. So in this kind of cases, we can't have a valid dependency structure. So by definition, if you want to model dependency in a graph, we have to use something that is called a directed acyclic graph. Okay, so firstly, it's a graph. So number two, it must be directed. Because if it is not directed, then it's naturally a cycle. Okay, so the third one is that it's acyclic, meaning that the graph doesn't contain any cycle. So for example, in this graph, there is no cycle. So there is no deadlock that could happen. Now, if that is the case, then we can define a structure that can reflect the dependencies between the vertices. We call this directed acyclic graph, or DAG. Okay, and DAG can be used to model different dependency structures. Now, once we have a directed acyclic graph, what we want to do, one particular application, is that we want to produce a sequence of the vertices that will allow us to do the vertices or the task in a given sequence. So we can think of it essentially as sorting a graph, right? So this, let's define this using an example. So you're given a graph that is the following sense, right? Just vertices and connections. And we are going to reflect this in terms of a sequence. Now, once you define a sequence, the sequence will respect the dependency structure such that when you line them up, all the edges are going to point forward. So here, these are exactly the same graph as this one, except that you put it in a sequence. And in this sequence, if you redraw all the edges are going to point forward. Now, this is significant. The significance is because once you align them up in that way, it gives you a sequence in which to consume or to execute the task such that at any point of time, by the time you come to a particular task, everything that it depends on has already been done. So here, for example, you do A first, and then you do G. By the time you get to D, you have done A, which D needed. And then you do B, and then by the time you do B, you have done A, which B needed, and so on and so forth. All the edges are pointing forward. Now in this case, for example, if they are courses, then it gives you the sequence in which to take the courses such that you can actually complete the prerequisites beforehand. If it is a task schedule, it gives you a schedule in which to do the tasks such that you can actually complete everything in a particular sequence. Now, you can think of it as actually sorting the graph. So you're given a graph and you're going to output a sorted ordering. Now, what does it take to actually sort a certain set of numbers? Now, when you talk about insertion sort, merge sort, right? Sorting means that we are going to output a sequence of numbers in a particular order. And there is no repetition, there is no missing thing, right? which means that in the topological ordering, you have to output all the vertices, and none of them is going to repeat. So which means that the valid output should be a sequence of the vertices, and every vertex will occur exactly once. Not more than once, not less than once, because it's just an ordering of all the vertices. So that's one, considering the vertices. The second, considering the edges. If you were to look at the edges, then all the edges are going to point forward. Now, there could be more than one such ordering. So this is a key difference between sorting an array of numbers and sorting a graph in terms of the topological sorting. This is a valid ordering. This is also a valid ordering, which is different. But both of them meet the same criteria that we have to sequence all the vertices, they occur exactly once, and all the edges point forward. Now, to solve this problem, we are going to employ a method that is called topological sort. Now, it's called sort because it's about outputting a sequence. It's called topological because the topology here refers to a map, which is the graph itself. Now, the way that its topological sort is defined in terms of DFS. Now, what does it mean? So this is the algorithm. So first, we are going to create a stack. And then we are going to process all the vertices in a sequence. For every vertex, if it has not been visited yet, we are going to start a DFS. So this is what it means. Now, why do we want to start a DFS for all the vertices? Because remember when we say DFS earlier, does it always visit every vertex? A single DFS from some starting point is not guaranteed to visit every vertex. But for topological ordering, you need to visit every vertex. The only way you can guarantee that is that you're going to try to do DFS from every single vertex to make sure that every vertex is going to be visited. Now, the difference here, right, so is that there is a series of DFS. Now, why do we call this DFS? Now, this is the DFS that is within the topological sort. Let's compare it to the previous DFS that we had before. So this was the original. Okay. This is the original DFS, right? And this is a DFS that is within the topological sort. Now, what is the difference? So first you visit the vertex, right? And then you're going to go through the neighbors in the adjacency list, and then you're going to extract the neighbor at I, and then it has not been visited yet. You're going to do traversal, which is recursion, right? So essentially, as far as the sequence is concerned, it is DFS. Now, what is the difference? The only difference is that there is a stack involved. And the stack is there to record the sequence in which you process a node so as to maintain the topological ordering. But as far as you're concerned, it is a DFS. Now, let's take a look at an example. So let's take a look at this example. So you're given an adjacency list, and what we are going to do is to output the topological ordering. So the first thing we're going to do is to create a stack. And let's say this is a top, right? So we're going to process this in terms of some DFS. We're going to start the first one, which is A. So we start DFS from A. A goes to B. B goes to C. C goes to D, D goes to F. Now F here doesn't have any neighbors, so it will return to D, right? Now upon return, we are going to go into the stack. We will push it into the stack upon return. Now D has not a neighbor, so then D will return. Upon return, D goes to the stack. D returns to the C. C has not a neighbor, so C will return. Upon return, C goes to the stack. Now we process B. Now B has done C, is now going to D, but D is already visited, so then it will move on to E. Now E will go on to D, but D is already visited, so E returns back to B. So upon return, the E goes to the stack. Now B has no other neighbors, so it will go into the stack. And finally A, at the end of it, upon return, is going to go to the stack. Now the stack at that point of time would give you the topological sorting. How do we know that it is a valid topological sorting? Well, firstly, A has all the vertices. There are 6 vertices here, and there are 6 in the stack. Secondly, if we look at all the edges here, and we try to reproduce them in terms of this ordering, so we will see that all the edges are pointing forward. So for example, A to B and C, A to B, A to C. B has edges to C, D, E, so B can go to C, E can go to the E, E can go to E, all pointing forward. C to D, D to F, E to D, and F goes nowhere. So all the edges are pointing forward. In that case, then you have gotten a valid topological ordering. If any of the edge points backwards, then is a wrong one. Okay? Now, any questions so far about topological sorting? So it is one of the algorithms that tries to output a sequence in which all the dependency relationships are respected, and it does that through a sequence of DFS. And every DFS is going to insert some vertices into the stack so as to ensure that upon return, it will go into the stack such that anything that is going to appear before that is going to be done later.